So I've been very excited to get to use glowscript.org in my physics classes because it runs VPython inside of a browser window. There's nothing you have to install. There's nothing the students have to download or file extensions they have to worry about or any of that. They can just type and run their code. But it doesn't have all of the full functionality that your standard Python does. And it doesn't currently permit the importing of external libraries. So whatever you want to use beyond the sort of standard calculation stuff, you have to create. So what I want to do today is create a class of complex variables. Complex variables are important because they show up in electromagnetism and in quantum mechanics. Just as a quick review, a complex number, here we've got a complex number z, is really two numbers sort of mashed together. It's got a real number a and a real number b that you combine in this combination of a plus ib. So this I here, this is the number that if you were like me in 6th grade, they told you that you couldn't do, taking the square root of -1. Well, it turns out you can do that. You just call it a new number I, and it turns this thing into an imaginary number. And so what we do is we say a, this part here that's not getting multiplied by the imaginary number, we call this the real part of the complex number, and we call this b here the imaginary part. I'm not going to write out imaginary, I'm just going to call that imag, so that way this name has 4 letters, this name has 4 letters. Now, one thing that I find students often run into is that they think that IB is the imaginary part. No. B is the imaginary part. The imaginary part is the thing that gets multiplied by I. So it's a little bit counterintuitive that the imaginary part is still a real number, but it's the imaginary part because it's the thing being multiplied by I. And these complex numbers are really important. There's a lot that you can do with them. Actually, there's a lot you need to do with them to use them in a physics application. One of the things you need to do is be able to separate them into their real part and imaginary part. That's pretty straightforward. Another thing you sometimes have to do is write them in terms of their modulus. So you can think of this as like the magnitude of the complex number. So this is going to be square root of the real part squared plus the imaginary part squared. So if that looks familiar, that's because that's just a Pythagorean theorem applied to a complex number. There's another thing called the phase of the complex number. We'll call that phi for now. And that's going to be the arctangent of the imaginary part divided by the real part. And the reason you want this phase is because another way that you can write a complex number is as the modulus times e to the I times the phase. And so when you use Euler's formula, this becomes a plus ib again. There's another thing you have to do with this, and that's take the complex conjugate, z star, and all that is taking all of the i's and flipping them to a negative. So it becomes a minus ib. So the real part stays the same, the imaginary part flips to a negative. Or if you like, in the Euler version here, this becomes modulus z e to the negative I phi. And it just flips the I again over here. So we would like to have a type of variable in VPython that can do all of this, so that we can maybe do some quantum mechanics and some complex electromagnetism stuff. So what I've done is I've gone ahead and started a class. We're going to call it CV for complex variable. And if you're not familiar with how to set up a class in Python, check out the video in the description below to get a little bit of an overview. Anytime you create a class in Python, you have to start out with this function init. And basically in here you put in all of the inputs. So the only inputs we need for a complex variable are the real part and the imaginary part. And so what we have to do is we have to attach those two values to the self. So we're going to say self.real equals this thing we passed in as real, and self.imaginary equals the thing we passed in as imaginary. And so now that we've got that, we've got these two values attached to that complex variable that we've defined, and now we can use those two down here and all of the other things we need to do with a complex variable. So for example, here we want to get the modulus. As a reminder, the modulus is square root real part squared plus imaginary part squared. So we come over here and we're going to say return square root of self.real squared plus self.imaginary squared. And so here what I'm having to do is anytime I want to reference real and imaginary, I just say self.real, self.imaginary, because I have attached those properties to the self up here. Same thing down here with a phase. We can return the arctangent. Now there are two options for arctangent in a Glowscript. One of them is just to a tan of a single thing, y divided by x. And that works fine unless you end up with y divided by x. I'm already anticipating what I need to do next. And that's fine, but one of the things you run into is what happens if x is 0. It doesn't really know how to handle the infinity. And so that's where a tan 2 comes in. With a tan 2, it takes two arguments. It takes y comma x, so it takes the opposite side and then the adjacent side, and then it knows how to handle x equals 0 a little bit better. Now then we got the conjugate down here. We have the complex conjugate. This part's a little bit more nuanced because the complex conjugate is returning to you another complex variable. So here the modulus is always a real variable. In fact, it's always a non-negative real variable. And then here you got the phase, and this is always going to be a real number that pops out. But the C star is going to be a complex number, so I need a complex number to come out. So I need to return a new CV, a new complex variable, and I need it to have the same real part, but the opposite of the imaginary part. So I just say self.real, self.imaginary, and put a negative in front of self.imaginary. And this is fine. It will return, it will self-reference this thing just fine. That won't be a problem. And so now I've got all of the basic functions I need. I've got the modulus, I've got the phase, and I've got the complex conjugate. Now there's one other thing I've added here, the string part, because if I simply define the class like this, and then ask the computer to print a complex variable, let's say with real imaginary part 1, 1, it's not going to return to me anything useful. Let's comment out the string for right now. So if I just do this, if I say print CV 1, 1, it gives me this, because this is what Python stores that class as. It says, oh, real 1, imaginary 1, that part is useful, but the rest I don't really have any way of using, right? So the rest is kind of useless to me, especially if I'm using lots of complex numbers and need to be able to sift through a lot of them. And so what I can do is I can define a function called string to have it display the complex number in a way that I can read it. So let's have this return the string of self.real, because the way you would write this is this real part plus the I times the imaginary part. So let's say plus, and then we need some text, plus I plus the string of self.imaginary. There we go. Oops, sorry, that shouldn't be in quotes, should it? There we go. So it's going to take all these three and concatenate them together. If you're not familiar with how strings work in Python, have a look at the other video in the description below, the one about strings. So here we've got the real part plus I times the imaginary part. And now what I can do is I can say dot string, open parentheses, close parentheses, and this will show me 1 plus I times 1. Yay, and that works out well. Except, of course, this imaginary part could be negative, right? If I make this a -1, Control 2 to run, I've got this weird 1 plus I -1 thing, and it really reads as 1 plus I minus 1, which is just I, and that's not what I entered. So what I can do is I can have this thing return different values based on or different formats based on the value of self.imaginary. So let's say if self.imaginary is greater than or equal to 0, then we'll have it return this as usual. And otherwise, all I have to do is change this to a negative. And then what I can do here is instead of having the imaginary part, I can have it be the absolute value of the imaginary part. And it's okay to take absolute value of this because this is a real number, right? This is not the complex number itself. So now I should get out something that makes a little more grammatical sense. 1 minus I times 1. There you go. And so you can change these to whatever you like, maybe square root 2, and it will print out for you the thing that you expect, 1 minus I times square root 2. So let's go back and run just a few checks to make sure this thing works the way we expect it to. So let's call z a complex variable. Let's make this one, let's make it square root of 2 for the real part and square root of 2 for the imaginary part. Cool. So the modulus of this thing should be, actually let's make it 1 over square root of 2. There we go. 1 over square root of 2. So let's make the modulus of this, let's have this thing print z dot modulus. And since this is a function, I need to put in open parentheses and close parentheses. And that should give me a 1, because 1 over root 2 squared plus 1 over root 2 squared square rooted should give me 1. Control 2 to run. And there we go. We get a modulus of 1. Let's check out its phase. Print z dot phase. And let's see, these two are equal, so that should be a 45-degree angle. Why it's not defined. Oh, whoops, I left these as y and x. So self.imaginary and self.real. There we go. Sorry, I was blindly copying from the documentation. There we go. I believe that's pi over 4. Yeah. Yeah, that looks about right for pi over 4. Let's see here. Let's have it calculate pi over 4. Yeah, 0.785, 0.785. Okay, great. Okay, one other thing let's check. Let's check z dot conjugate. Conjugatia. Control 2. Oops, sorry. I've already made a mistake. So I've called the conjugate. It gave me the gobbledygook I don't want. So I have to say dot string, open paren and close paren. And this is okay because it takes this chunk as a new complex variable. And so it's calling the string part of that, or the string function of that. And there we go. There's our complex conjugate. We've got 1 over root 2 minus I times 1 over root 2. And now let's run a little bit of a check here. Let's call z star equal to z dot conjugate. So now I've got the complex conjugate of z there. And let's have it print for me, please. Z star dot modulus. And let's do a control 2. And there we go. We've got a 1 here. So it gives me the same modulus, because a number's complex conjugate will have the same modulus, because when you take that square root a squared plus b squared, you end up with you end up squaring away the negative, so it doesn't matter. There are a few other things we'll need to be able to do with this, like adding complex numbers, subtracting complex numbers, and multiplying complex numbers, but I think we'll get into that in a future video. So thank you so much for watching. I will see you next time. Bye-bye.